Today's talk is going to be very simple, a little bit of history, the characteristics of cosmic rays, detection methods, observatories, because that's interesting as well, and the instruments we have at Mount Burnett. Now, the references I've got here, there are 3 books. One of the things I like to do is to find a subject and get a really old book and get a new book, because it's just great to see the changes. The one with 1936, that's when the Nobel Prize was awarded. So the book was written before the Nobel Prize, and it was espousing the virtues of Robert Millikan, who didn't get the Nobel Prize for that. But no, these are some books there if you're interested. But the one in the middle is actually the one my favorite, actually, out of all of those. I think 1989, it was sort of a good time. Anyway, let's go. The beginnings of something strange. Now, cosmic rays, we can't feel them. And so how do we detect them? And it was something mundane. And that was, I'm not sure if when you went to school, whether you had electroscopes. The one over here, I'll just see if I can, yes, the one over here that's like the one I had at school that you would use, and you would do some static charge, and the gold foil would move up and down, and you could discharge it and it would close. It's quite simple, but there was a bit of a problem, and that was that you could charge it up and it would go out, but you left it for a while and it would slowly discharge. And so people thought, oh, there's obvious problems in construction or something like that. And they thought, well, and then something came along and it was called radioactivity. And so Becquerel, the Curies, they came up with radioactivity and thought, well, maybe it's something to do with ionization, and that's the reason why it discharges. So let's put it in a big lead box. That will fix it. It'll stay there. It didn't. They put it in a mine shaft. They went, okay, let's go down. Maybe it's something in the atmosphere. We went down to a mine shaft. That didn't work. All right, let's try it under a lake. Maybe in a box with a fox or in a train in the rain. They tried everything, but eventually they did find something that changed it, and that was they went up to a mountain. They went up to a mountain, and it sort of was it decayed quicker. So they thought, well, maybe there's something to it. So they had balloon flights, but the balloon flights were a bit inconclusive until there's one person, and it was Victor Hess. And I like this picture here because it's got all the kids around it. I think it's wonderful that, like, in 1911, having a balloon flight must have been an amazing thing to see. And so I think the description of Hess is meticulous. And that was that, unlike the other balloon flights that showed nothing, he compensated for pressure. He used reference sources on the ground when he returned, and he used multiple electroscopes and repeated measures. He did it a couple of times. And finally, he got a graph. And that was enough to convince most people that there was cosmic rays were coming from somewhere in the sky. There were a few people that disagreed and thought that maybe they came from the mesosphere, but it was one of those, it was a pivotal moment. Now we've got a Nobel Prize 25 years later. It didn't come via Australia Post. It wasn't for that reason. But what happened was that the real reason is that they knew that it came from up high, but they didn't know what it was. Now there's a lot of work was done between 1911 and 1936 when the Nobel Prize was awarded. And the first thing that sort of happened was cloud chamber experiments. So they could actually do things where they could put a magnetic field, or you could put shields of lead or other materials and measure what was going to happen to particles. Also, I'm putting here Rossi because Rossi is a bit of a favorite of mine, and he used Geiger tubes, and he worked out that the particles were charged. He worked out that where they came from, the angle of incidence, things like that. So in 1936, the Nobel Prize was awarded both to Victor Hess and to Anderson, and that was because they knew where they were coming from and they knew what they roughly were, and that was that they were muons. And so when we talk about cosmic rays, we're sort of talking about 2 things. We've got a primary cosmic ray coming in, but then it hits our atmosphere and shatters. That's why I've called it celestial bullets. These are not like where you have a billiard table. This is like getting a gun and shooting the billiard ball. It shatters into subatomic particles. And so as you can see here, there's the positron, which is one of the things that Anderson discovered, and the muons, which Anderson discovered as well, I think with somebody else. But as you can see here, there's a lot of interactions as the cosmic ray comes in, and it's illustrated with this nice little simulation here of showing that it comes down in a cone. Now, in the early days of cosmic rays, it was all about particle physics. It wasn't about astronomy. So astronomy comes along a bit further later because the issue is you couldn't tell where things were coming from. This is probably the most important picture of the whole presentation. And that's because at the top, you've got where cosmic rays come from. They're either solar generated, galactic, or extragalactic. And when I mean that is they're coming from a supernova event. Now, a supernova event of a fairly large size, roughly 8 solar masses upwards. And when it collapses and explodes, there has to be a magnetic field to accelerate the particles out. They've done simulations and it needs to have certain combinations for cosmic rays to come out. The second thing is the energy. It's 14 orders of magnitude. This is a little bit hard to do sometimes with measuring equipment. So they have to use several layers of measurement to try to work that out. The rate depends on energy. So there's that nice sloping curve. As you can see, there's sort of like events like the low energy solar ones, which are like, 1,000 times a second. And then you've got other ones in the middle that like happen once every birthday. And then you've got ones down the other end that happen once a century over an area of 1 kilometre. So the equipment I have here is very unlikely to capture one of those magnificent events because it's just so small. But the other thing as well is that there's primary or secondary. So primary ones are, generally speaking, we'll talk about it in a moment, is that they're protons. They're coming in really fast. They then, as you can see with the orange, they then shatter into a cone of subatomic particles, which we can detect. And so if you're in space, you'll be tending to detect primary or via a balloon. And the path of magnetic field, if you notice the lines, some of them are curved and others are straight. The more energetic, the straighter it is. So the extragalactic ones, it's sort of almost survival bias in a way, is that it has to be a higher energetic particle from a distance to be able to detect it. And so that is part of the story. Now I've got that curvy line. That is basically on one axis, you've got flux, on the other axis, you've got energy. Now, just as for an example, if you have a look, there's the LHC, so the Large Hadron Collider. The amount of energy it can produce is nowhere near like what a cosmic ray can produce. And that was one of the things in the early days of cosmic rays is you could use them for particle physics experiments. The problem is, if you want to detect something really high energy, you have to have, as like we're talking about before, kilometre and wait like a century. So they're very hard to get. Now we do get them because we do have some large observatories. Now the other thing with the curve is if like scientists will look at it and go, well, there is a curve, but there's kinks in it, and the kinks are interesting. So the first kink where the blue starts, it's what they call the knee, and that is the knee, and it's sort of postulated that that is where there's a change in the way that the cosmic ray is produced, and that is it's a larger particle size. And the ankle is basically where you're starting to get extragalactic cosmic rays coming in. Now there's a thing they go, OMG, oh my God particle. The oh my God particle, basically, if I could just have to point to it, is roughly there. It's not on that graph. And so the oh my God particle, so I really do, oh, here we go. So it's further up here and it's right there. Now, I'm not sure if you noticed, but this says local void. In where we are in the universe, we're kind of like the last petrol station on the Nullarbor. We're right next to a big lot of nothing. That might explain the Fermi paradox. But the issue is that out of the desert is the highest energy particle we've measured. So there's something either on the other side of the void that's generating it, some sort of massively huge supernova. And that's probably what it is because there's nothing much in the void.
When you say we, do you mean our solar system or our galaxy or?
Yeah, our galaxy and neighbouring smaller galaxies as well. Yeah, there's a local void. There's some other voids as well. There's sort of the known universe has sort of pockets where there's a low density. And so but we happen to be right next to one of those low density pockets. And so I kind of like that because it may be the reason why we have life. And that is you don't, getting brought up on a farm compared to being brought up in a city, it might be lower risk. I don't know. It's just an idea. No, it's basically it's the highest energy cosmic ray that's been detected, and it was detected in one of the. I will show you in a while, just one of the larger facilities because it really needed to be over several kilometers where they detected it. Now, we talked before about there were primary cosmic rays that they're going through a galaxy, and then secondary when they hit our atmosphere and shatter into that cone. Now, the primary cosmic rays are mostly hydrogen nuclei and sometimes helium. There's probably hydrogen's roughly 90%, 9% helium, and the rest of it is the 1%. Now, the interesting part is that generally speaking, if we measure out in space, we've got very little lithium and beryllium and boron, but there's a lot more with cosmic rays. And that's because of spallation. So in other words, they hit each other and shatter, bits come off. And so you do get those ones. So that's kind of interesting to know that the cosmic rays are coming from the galaxy, but they also hit each other and degrade. Now, the highest reported number is 92. So that's if you think of the atomic number. Now, as I said before, there was Rossi detected that they were positively charged. And that's an easy experiment to do. You can actually do it with this instrument here. And that is that you can have two detectors and you can change the angle. And what you'll find is that there's a skew. And that's if I remember, there's a rule with a right-hand rule where you have a look if you've got a magnetic field and you apply a charge. And that's what happens. So with us, we know that primary cosmic rays are positively charged. Now, I said mostly there are some exceptions, as there always is. Now, this is where I like is the detection. I'm an engineer, so I like to be able to measure things. And so as we talked before, is we've got this cascade coming down, but there are several different methods. We can detect that they will actually generate radio waves. It's not a large source, but you can actually detect them. There's electromagnetic emission for Cherenkov. And the only problem with that is that it's very dim, so you can only measure it. You have to have very large telescopes, and it can't be a moonlit night. But they still do measure it. And muons, which is the easiest thing to do because you can use ionizing tubes or scintillators. Now, this is sort of more of a historical, but cloud chambers were one of the first ways of measuring cosmic rays. And they actually sent up balloons that had automated cloud chambers and cameras. So they synchronized the pressure and they would take a photo and all those kind of things. It's an old way of doing things, but if you've ever seen one in action in live, they're wonderful because you can see the particles spin by and there's this little whiff of vapor. And so it was one of the things we wanted to do at Mount Burnett, but we just haven't got around to it because the person I was going to do it with was a photographer and we were going to make a system up, but it didn't quite get to that stage. But it's a historical method. Photographic emulsion, I've got a little bit of a soft spot for the people who did this. So if you can imagine what they did is they stacked up a whole lot of film, put it in a box, sent it up, took it down, and then they developed it. And then they had to actually painstakingly take each slide, develop it, and then look at where the trace went. So as you can see in the other one, this diagram here, that is where they've cut out the bit where they could see that, oh, it's gone off in this direction. They cut out that bit and then they find the one below it and then stack it on top. And then they put it all together. It took days and months to do, but it's what you have to do. So it was, but this is something I don't want to do. So, but I think it's wonderful that they did it. Ionization. Now, ionization is generally how at Mount Burnett we do it, and in the early days. So the interesting thing is that Rossi's experiments were 1923, so it's kind of like our first cosmic ray is in 2023. So I think it's kind of funny that it was 100 years later and we're still using the same tech. But one of the things about using ionization is that it's electronic. So it was very easy to do automated equipment. So they used it in the first balloon flights. Of course, spacecraft like Sputnik 2, Explorer 1. I've used Sputnik 2 because Sputnik 2 would have discovered the Van Allen belts. It was actually interesting, Australia had recorded the Sputnik 2 going over, but the Russians wanted the information, but they said, well, what's the information about? And the Russians didn't say. So the information wasn't released. Had they released it, they would have been the first to discover the Van Allen belts. But history is different than that. They can be used in arrays or layers, and you can do things where you actually have plates and you can have sparks, and they're quite interesting. But the issue is that they're an all or nothing response. So there is, whether it's high energy or medium energy, you still will just get a trigger or no trigger. And of course, we use them at MBO. Scintillation is another method, which is using either, normally you would use plastic, you could use crystals, but there's the plastic, and the good thing about scintillation is if you've got this flat plate, you can have quite a large area and you have something that detects light. And when the cosmic ray comes in, it illuminates for a second little flash, and you can detect that. And there will be a proportionality to the amount of flash you get. But of course, we're talking beforehand, there was 14 orders of magnitude. You will not get that out of a scintillator. You'll get a little bit, but not too much. But it's still quite useful, and it can be formed into shapes, which is important. Now, we've talked about detecting, but the other thing you want to do is measure something, the energy of it. And one of the easiest ways to measure something that's going extremely fast and extremely energetic is to try to stop it. And so you have these layers, and the particle will come down. You'll measure it. Yes, it went through this one. There's another layer. Oh, did it go through that one? Yes, it did. And you can keep on going until it completely stops. And so that's a colorimeter. So they are used essentially to tell you how energetic it is. And the other ones, like say, for instance, the scintillating arrays or the ionization tell you the position. And there's one last little nice mention here is Cherenkov. I'm not sure if you know what the Cherenkov is, but you've got the speed of light through vacuum, but the speed of light through water or glass is slower. So if you've got a particle that's going quite fast and is going faster than the speed of light through the material, it will have to effectively release energy in the terms of this Cherenkov light. And so there's that blue image there is like a reactor. And so there's this one over here this is in Japan, and they have basically a huge tank, and it's covered with photo sensors around it, photo multiplier tubes, and they fill up with water. And when there's a particle that comes through, it generates Cherenkov light, but Cherenkov light is like a shock wave. And so it creates like a cone of light. And with that cone, as the light travels, you'll get like a expanding donut on the detectors. You'll get this picture. And so you can tell which direction it came from. There are other ones like that just want to detect yes or no. And so in this example here, you've got like a whole bunch of tanks of detectors. And effectively, this is like a big retina over a kilometre or so. And you're trying to detect when a cosmic ray comes in and its other muons that are coming through. And if you have these telescopes, you'll look at Cherenkov light. So you'll have Cherenkov detectors in tanks, and you'll have Cherenkov detectors looking at the sky to try to give you the path of the cosmic ray coming through and how big it came, how energetic it is. Now this is going back a bit. There's a thing called a hodoscope, which is basically hodo, I think, is derived from the Greek meaning path. And so if you could imagine if you had a whole bunch of ionization tubes and you stack them on top of each other, if a particle came through, you'd get them triggered. And this was demonstrated in the 1933 World Fair. This thing here is a miniaturized version of it. And so if you see the flashing lights, there's 19 Geiger tubes in a stack. And what happens is that you'll get like a line of them going off in different angles that will trigger. And so if you, it's kind of hypnotic to watch, but the only thing about it, of course, is it's low resolution, but it's 19 tubes. And so 19 Geiger tubes plus power supplies plus electronics, it costs a little bit. So I didn't want to go the whole 10 by 10 array that they did in 1933. But as you can see here, it's quite a large instrument. But what they tended to do was actually just use a minimalized array in balloon flights. And so if you could imagine, there's a stack of tubes and you want to know which angle it's coming through. And as we talked about before, this is like a colorimeter. So you have stacks of lead plates and detectors in between. And so you're detecting how many plates does it go through. So you can work out which angle did it come from and how intense is it.
Actually measuring cosmic rays now.
It is, yes. Yeah, so you're seeing cosmic rays come through. This one is detecting cosmic rays. So there's a counter saying if there's a cosmic ray coming right through the middle of it, any other cosmic ray won't be detected. So, but yes, that's detecting cosmic rays. And so it's kind of fun to watch because you will see like, oh, hang on, that actually did. There's 4 of them triggered or 3 triggered. So it's more of a demonstration one. It's because we have at Mount Burnett, we have a lot of time where we educate children, will come in, scout groups, that kind of thing. And so it's interesting to show cosmic rays that you can actually have an angle where they're coming through. We would love to have a cloud chamber. That would be even better. But that's kind of the next thing you could do, and that is to show which angle they're coming in at. But there is an issue, and that is if you can imagine, there's tubes. The tubes have they're probably that long. So that means you might get something coming in, but it might be coming in at an oblique angle. So that's the only issue with this angle hodoscope is you're only getting angle in one direction. The way to get around that is to actually have them crossed. And if you could imagine, like there's 2 tubes that when a cosmic ray comes through, the top one will be an X and the bottom one will be a Y, and you'll know where exactly a particle came through. You can do it with scintillators, or you can even do it with scintillating fiber optics. And so that gives you a position. What you really need is to have 2 of them. So you've got a position at one and a position at another, and you can actually then get an angle. So you know that where the actual cosmic rays come from. And so this is kind of like, finally, to me, being in astronomy is you want pictures. Unfortunately, we'll talk about cosmic rays in a minute, but you can get at least some sort of imaging with 2 hodoscopes. And what you would probably do normally is you would stick a colorimeter at the back. So you would know where the cosmic ray came from and what energy it was. And in fact, if we have a look here, this is what they normally do. They'll have a colorimeter at the bottom, and then they'll have methods for detecting the angle. And so that was the ANZAAS, which is on the International Space Station. I think it's been decommissioned now. But the thing that hasn't been decommissioned is the Voyager. Now, the Voyager actually had this. Now, the Voyager cosmic ray is rather like this. It has 2 tubes, but they're each focused at different directions. And they're doing counts. Now, the interesting thing if you've got 2 tubes, which way does the cosmic ray go through? You don't know. It could go through either way. So you have to live with that. But the interesting thing I find with the Voyager one is that it had a design limitation for it could operate at. They were running out of power, so they said, look, let's turn it off and just see what happens. They turned off the heating and it still works. So 1970s design seems to be doing quite well. The other way, of course, is we talked before with that other pictogram, was that you could look at balloon flights. There's actually, in 2025, there are 14 planned flights of balloons, and one of them is a cosmic ray flight. I'm not sure in 2026, the US budget for science might be cut, so then But since cosmic rays are largely not to do with environmental or global warming, it might survive. But anyway, so what we've got is once again, photoscopes, you want to know where it's coming from, and a calorimeter, how energetic is it? Now, where a lot of the information comes from is the large observatories. And so the large observatories are over, as you can see here, there's like 30 kilometers in one direction. So each one of those little dots is basically a big tank of water, and they're measuring Cherenkov radiation as a cosmic ray comes in. So they've got like a big retina on the Earth. And they've also got other things like the Cherenkov telescopes looking at it when it's a dark night, and they can measure radio and things like that. And so there's the Auger, the Hawk, and I can't remember what the other one is called. What was it? Argo. They are in, I think, the US, I think it's France, and I can't remember where Argo is. But the weirdest observatory are these two. But these ones are probably the most interesting. So they're three-dimensional. So the ice cube, what they've got is they've got like the traditional large area cosmic ray telescopes where you've got surface detectors, but they've drilled down and they've got sort of arrays of detectors that they can detect in 3 dimensions. And it's the same it's effectively what they've done with the square kilometer underwater one, where they've got all of these little balls are photodetectors. They're looking in different directions. And what they're looking for is Cherenkov light. And they've got so many of them, and they've got some very interesting timing, and they can tell where it came from. And so they can get the direction of where the cosmic ray came from. I'm not sure why they've got whales in this picture. To me, that's a bit of like hopefully the whales don't get caught up in it. It would be a bit of a sort of jewelry for them. This is one of the ones I hate doing, because you go from these like complex observatories, and then there's sort of someone with a big pizza box. They actually do call it the pizza box. And this is, it's a great idea, and that is to have basically one tile, and inside that there's a big scintillator with silicon detectors. And what they're doing is they're detecting basically a cosmic ray and its relative intensity. And what they're doing is, the whole idea is with the Murchison wide field array or the square kilometer array, is that they can just put one of these devices on each location. So effectively it becomes like the retina on the ground, because they've got so many of them that you can pretty much measure cosmic rays, not for free, but fairly at low cost. There are some universities doing some research, but the University of Adelaide looks a little bit underfunded. I think it's I think it's for teaching largely, but they probably do get a few papers out. But this is the interesting one from my heart. There's the Antarctic and also Kingston, they've got a duplicate facility. And so there's an underground facility, which they've dug down to drop down sort of the background counts. And so they've got it's a bit like this. You've got basically 2 detectors. And in a way, what they've got is this whole set of tubes and another one behind it. So they're facing in a different direction, and they're looking for coincidence. But the one at the top on the ground is this one here, and that one's a zenith cosmic ray telescope. And if you type into Bureau of Meteorology, you will actually see they've got a link into it, and you can get the daily plots of the cosmic ray count in Antarctica coming from the zenith. And they're looking for the Australian Antarctic Division's sort of edict at the moment is look at things that are affecting the environment. And so in this case, the cosmic ray detector is looking for what they call Forbush decreases. And that is like looking for events of the sun that will actually change the amount of cosmic rays that reach the Earth. Because cosmic rays, as we said before, are affected by a magnetic field, and they're also affected by dense things. So that's what they're looking for. I put this one in, it's an interesting one, is that there's a guy called Robert Hart, and he's really into cosmic rays, but he's in it for art. And so he had a one of these things that like WOMAD or something like that at Adelaide, and he had all these little balls and they would glow. It would glow green. If there was only one tube that was fired, it would glow another color if two tubes were fired, and it would also make a sound and was controlling a synthesizer. At Mount Burnett, this is the last sort of getting towards the end. At Mount Burnett, this is what we have here. This is what we call a cosmic ray telescope, and it works basically having two tubes. And what you're after is when a cosmic ray comes through both of them and triggers both of them at the same time, what they call coincidence. So if we have a look at basically what it looks like is that there are two tubes, but what it does, it maps up onto the sky with a DA at the top, shows you the aperture of where we're detecting cosmic rays. And what we're doing is that our first experiment was to actually just change the angle. So every month we would change the angle and we look at the counts. And as you can see, the counts go down. So you get the maximum at vertical and you get the least at 90 degrees. Now the gray curve is ideal. The reason why it is actually offset is that when you go completely flat, you're getting cosmic rays from this side and you're getting cosmic rays from the other side. And we can't detect the difference because we're only like less than a meter apart, and that's really tight timing. But the main thing was that we worked out that the system is working. So the cosmic ray telescope was operational in 2023. That was that one there. We've, of course, upgraded a little bit since. But we also have some other ones. And so we've got this one here at the bottom, which you can see is the hodoscope, which is as you can see, it's an interesting instrument. But there are some other ones, and we've got a Cherenkov telescope, which is a much larger one. I was going to bring it along, but it works in an unusual way. You have to have water. Do you remember those flasks you would get and you pour coffee into, and they're sort of like got a little, they're made out of glass in the inside and they're vacuum sealed and they've got like reflective sort of silver coating? Yeah, thermos. Well, you put water in that, distilled water, and you plonk a photomultiplier tube into it, and you've suddenly got a Cherenkov detector. It's a small one, and it only just works, but it works. And so in those two tubes that you can see here and here, there's a thermos. And I didn't have any, so I went on eBay and I found some nice sort of fetching brown ones. And unfortunately, the photomultiplier tube didn't quite fit. So I had to actually sit down there painstakingly with emery paper and try to make it fit, but it worked. And so that's a Cherenkov telescope. So on a similar sort of action, except you can dial in the amount of like where you want your discriminator level to be triggered. The other one, which is here, you can see there's 5 tubes here. 5 tubes one way, 5 tubes the other. That's actually like a hodoscope. There are 2 of those, and the whole idea is to have an imaging system. You've got 5 by 5, 5 by 5, and you can tell which direction it's coming from. Now, these images down the bottom are from the big boy telescopes. We're probably at Mount Burnett are probably not going to get that kind of resolution. And the reason why is it's statistical. And while you've been sitting here, what number has the counter got on it? So it's measured 22 cosmic rays coming through there. So this is a very low resolution version. We're upgrading it to be sort of 10 times more. But if you can imagine, if you're trying to work out where the hot spots are, having 22 counts over half an hour is not going to be the greatest way to work. So we have to get better detectors, and it will take multiple samples. And that's the issue, is that if you look up into the sky, generally speaking, it will look isotropic. And that is that if I took a count, if we took, say, every hour we took measurements, you'd almost get the same figure. plus or minus a bit. And if you kept on doing that and averaged it, if you did that for a year, you'd get pretty much, it would look like a flat line as you looking at the sky. But once you go below 1%, you start to see hot spots. And that's what these telescopes show, these other ones. And that is that there is hot spots where there are, like beforehand, when I showed you that other picture where there was the, oh my God, particle and there was the void. As you can see here with the, that's roughly where the void is. That's where the void is. So we're getting like, this is sort of looking right, but then we've got some other hotspots. This line here is the galactic plane. So if we look there, and the other line, which sort of cuts through it, that's what we call the supergalactic plane. So we've got our galactic plane, that's the Milky Way, but we then say there's another plane where we've got the major galaxies, and it's purely arbitrary, but they defined it, and I think it's 84 degrees off our plane. But it's a good reference point, because if you follow that line, generally speaking, there's a bit of hot spots around it. So it is actually showing that we are getting particles coming from some of the larger clusters around our own galaxy. And so that's where we're going next. We hope this is something that's just rendered. I took another diagram and just depleted it down to a lower level. But we'd hope if we can get within 10 years that we can get some image that looked roughly like that, we'd be very happy, because that would indicate that we have got our systems working, we've got compensation, and a bit like Hess, and that is to try to make sure that we're a bit more meticulous and have references, calibrations, those kind of things, and we should be able to get something. And not a lot of amateur groups have done this, and that's what we're looking at.